All right, so here we are. Let's get into this first type of equilibrium problem where we're going to actually be using equilibrium concepts to solve for particular concentrations of stuff at equilibrium. So it starts off with saying acetic acid is a weak acid. And that means since it's a weak acid, we have to treat the ionization of acetic acid as an equilibrium reaction. And so we want to know what the pH of a 2-molar solution would be. And so the first thing we have to do is write down the reaction. So we let acetic acid disassociate into water, into H plus and its conjugate base. Now it's probably helpful to go ahead and add the states in there so that we know what to include in our equilibrium expression. Now we start off with 2 molar H2 or acetic acid. We don't have any of this and we don't have any of that around. So no H plus, no conjugate base, no acetate. And so what are we starting to do here? This is our good old ice table. So we want to think about what happens to acetic acid in terms of its initial concentration, how it changes, and what it'll end up being at equilibrium. So the change is minus X, right? It's going to go down by some amount. H plus will go up by the same amount, and so will acetate. And so at equilibrium, the concentration of acetic acid will be 2 minus X. It'll be X for H plus, and it'll be X for acetate. Now, what was that equilibrium expression again? It's the concentration of the products times over the concentration of the reactants raised to their stoichiometric coefficient. And if I want to know the pH, then ultimately I have to figure out the concentration of H plus. And so that's what we're going to use the equilibrium expression to figure out. So what am I left with? I'm left with the equilibrium constant 1.8 times 10 to the negative fifth equals X squared over 2.0 minus X. And we sorted that out from the ice table. Now let's make some room here. Let's kind of get a little bit of extra space. And what's the deal here with the formula that we just wrote, though? The algebraic expression that we just wrote based on the equilibrium constant and the ice table. Well, if you look at it, it's a quadratic. And it's not a quadratic that can be solved with tricks like constant, like perfect squares on both sides or something like that. You would definitely just have to solve for the quadratic equation in order to figure out what X is equal to. Now that's certainly a possibility. And if you do that, you will get the right answer. But you can also do a shortcut, and you'll need to apply this shortcut most every time you can. And if you can't, then yeah, you're gonna have to go ahead and use a solver or do the quadratic equation. But here, let's assume that X is small. How small do we want to assume X is? We want to assume that X is so small that when I subtract X from 2, I essentially get 2. Excuse the fact that I don't have an E in assume. Okay, so what happens if I make this assumption? Then this boils down to 1.8 times 10 to the negative fifth equals X squared over 2, and that I can solve, right? So then I get X equals 0.006 molar after I multiply 1.8 times 10 to the negative fifth by 2, and then take the square root. Okay, so let's see, is X small compared to 2? Well, yeah, it is. If I subtract X from 2, then I get 1.994, and that is essentially 2. And so the assumption is valid in this case. So I'll go ahead and I'll write down the pH by taking the negative log of 0.006, and I get the pH equals 2.72, and that was the answer for the question. Okay.